Hello, this video is the final code circuit review for Elizabeth Limer to accompany my final paper. Here are the design goals we wanted for the multi-channel oscilloscope. My main contribution to the project was the SPI and serial communication. Here's a graphical block diagram of how that's going to work for our oscilloscope. Here is the full software block diagram. You can see the SPI communication lines in yellow, the serial 1 communication line to the live oscilloscope data on the serial plotter in green, and the serial 2 communication between Python on the computer and Arduino code on the Teensy to pass user settings and capture data back and forth. There's some code flow important details that I'll address a little bit later. You can see we're minimizing the loops within the Arduino code and using mostly if statements. Since the midterm report, the SPI communication had to be rewritten for the ADC chip used in the design of the ADS8634. The previous testing was on an easy-to-find through-hole 10-bit ADC chip, the MCP3008. The first adjustment was to change the number of sends between the Teensy and the ADC. The MCP had a 3-send communication and the ADS had a 2-send communication. The ADS chip also required some setup to use the internal voltage as the voltage reference, configure some pins, and use the automatic channel cycling feature. The ADS automatic channel cycling made a more complex rewrite to capture the correct channel data from SPI reads. So the MCP would just send the channel that you wanted to get. On the ADS, if you have it on auto setting, it will just automatically cycle. So we had to actually capture the channel data and convert it to get the appropriate readings. For serial communication, to get the user settings from Python GUI to the Teensy, the Python PySerial communicates very well in single characters. So rather than sending the channel settings in a 8-bit stream, I created a dictionary to match a specific letter to each possible channel setting, and then have that be a single character to send over to Arduino. And then on the Arduino, the single character gets decoded back into the channel setting. The rest of the user settings are formatted in a single character format and sent as a string over to Arduino. And on Arduino, we have a character string to capture the user settings coming in. To send the converted analog readings on the Teensy over to Python on serial 2, the multiple serials are, I believe, unique to the Teensy. Can operate in single, dual, or triple serial mode. So here I'm calling serial.usb1 serial 2. So Python, when I was working on this, corrupted the data if I sent more than 100 data points. So I just split up into 5 different sends to make sure that we would get some clean data going over to Python. Final serial communication was to send the captured data points to the serial plotter on serial 1. It's the main data line between the Teensy and the computer. So a couple formatting things to have this emulate an oscilloscope screen. First, to scale the analog voltage number to the vertical user settings that have come in from the GUI. Second, to prevent the scaled voltage from exceeding the plus or minus 20 volts so that the screen won't be jumping around or giving data that was exceeding the capabilities of the scope. And then finally, to map the analog reading that was scaled to the digital range of 0 to 495. And that digital range is from the 12-bit number that has come in from the ADC. The serial plotter y-axis is not settable, so to hold the screen steady, a digital 0, the digital halfway point, and the digital max, which was modified from 4095 to 4000. This kept the window looking a little more clean. These values are printed on every send, and this holds the serial plotter screen steady. This modification to the max digital value was only done on the serial plotter. The GUI screen, since it was more customizable, was kept to the more accurate value of the 4095 max. Here are the testing and troubleshooting tasks that I did. First, I built and tested the circuit on a breadboard for the full system functionality to make sure readings were coming in properly, you're getting good digital data, analog signals are clean, everything's functioning properly. So on the USB powered breadboard, noticed there was a lot of noise in the boost circuit, corrected it with a better layout and some improved filtering to get a nice signal that we could work with. For testing the proper capture and convert of ADC data back to analog values, used a couple function generators that I have and tested their values and waveforms against a commercial oscilloscope that I also have, and had good agreement of data. I wrote a small test program to make sure the GUI settings were coming in properly on the Teensy. Here's the results of that, showing the agreement of data between the two softwares. Code flow between the Arduino code on the Teensy and the Python on the host computer was important to make sure we got a max sampling rate for all 4 channels, and also timely capture of user data. So here's the little screenshot of getting a 200 kilosample rate for all 4 channels. This rate was made possible by using both an if statement to capture one sample at sample rates below 150 kilosamples per second, and also using a for loop to capture all 500 samples continuously at rates above 150 kilosamples per second. After the one sample at the lower sampling rate, the Arduino will loop back to the beginning of the main loop to check for the new user settings. The trigger was tested in all its different modes: rising, falling, higher, lower, and free run. Here's a screenshot of the rising and falling trigger modes. Here are the final tested specs for the multi-channel oscilloscope. And the following slides are the demo videos that we showed in class, again, just to have them all together with everything else. Thank you.